In this video, we will go over some very basic examples of how to use CCASM. The two main examples we will cover will be how to generate an arbitrary qubit state and how to generate the 2-qubit Bell states. An arbitrary qubit state can be represented as a superposition of two basis states. Here we use the 0 and the 1 state as our basis. Instead of using two complex numbers, alpha and beta, to describe our state, we can equivalently use two angles, theta and phi, to fully represent the state of our qubit as shown here. On the right, we show what these variables represent on the Bloch sphere. By convention, we take theta to represent the angle between the state and the positive z-axis, and phi to represent the angle between the state and the positive x-axis. The value of theta essentially represents the amplitude of the basis states of our qubit, and phi represents the phase of our qubit. On this slide, we show some examples of qubit states and which values of theta and phi would correspond to them. For the 0 and 1 states, we simply take theta to be 0 or 2 pi. We put values of phi equal to 0 here. However, in practice, phi can take on any value here since the phase of the qubit state is irrelevant at the poles of the Bloch sphere. For the plus and minus states, we take theta to be pi over 2 and phi to be 0 and pi respectively. For the plus and minus I states, we take the same value for theta and set phi to be pi over 2 and 3 pi over 2 respectively. Essentially, when starting from the 0 state at the north of the Bloch sphere, all we need to do is to perform at most 2 rotations to obtain any arbitrary state. One is a rotation of an angle theta, which we define by convention to be about the y-axis, and the other is a rotation of an angle phi about the z-axis. It should be noted that the order of these rotations is irrelevant, and the rotation by angle theta can be equivalently performed around any axis in the xy plane. Next, we will see what these rotations look like mathematically. So, to obtain any arbitrary qubit state, we require these two operations, the y and z rotations, which we represent in matrix form here on the slide. First, let's consider an initial state of 0. If we perform a y rotation of an angle theta, we obtain the following state. Next, if we perform a z rotation of an angle phi on this state, we obtain the next following state. If we remove a global phase of e to the minus I phi over 2, we will obtain the state that we want. Here, we have shown mathematically how to obtain any arbitrary qubit state on the Bloch sphere by utilizing 2 rotations, starting from an initial state of 0. Now, we will show how to generate an arbitrary qubit state on CCASM. We start off with specifying a single qubit and preparing it in the Z basis. Then, in lines 7 and 8, we apply the arbitrary Y and Z rotation. First, we specify the qubit which this gate is acting on, and second, we must specify the angles in units of radians. Here, we use theta and phi to be pi over 2 and pi, or in radians 1.57 and 3.14 respectively. We can see that the corresponding circuit on the right. These gates will generate the minus state as shown in the previous slide. To generate any arbitrary state with some theta and phi, we must replace the values of these angles. Now that we have seen how to generate an arbitrary qubit state, we will move on to generating the 2-qubit Bell states. Bell states are examples of maximally entangled 2-qubit states. In total, there are 4 such Bell states, called the phi plus or phi minus and psi plus or psi minus states, which are given by the expressions here on the right of the slide. Together, these 4 states span the full 2-qubit Hilbert space and have useful applications, particularly in the field of quantum communication. In this slide, we present the quantum circuits used to generate the Bell states. Here we see 4 different circuits, each corresponding to their respective Bell state. The main components we need to generate a Bell state is the Hadamard and C0 gates. Before the dashed lines in the circuits, we use a different combination of X gates to prepare our qubits in the 4 basis states of 00, 01, 1, 0, and 1, 1. For example, to generate the phi plus state, we simply perform a Hadamard on the first qubit, followed by a C0 with the first qubit as the control and the second qubit as the target. For the other Bell states, we provide a different initial state using the different combination of X gates. Now we will go over how we can use the circuits presented in the previous slide to generate any of the 4 Bell states on CQASM. Here we have 4 pieces of CQASM code with their corresponding quantum circuit and Bell state. We can see how easily implementable these circuits are on CQASM. The circuits consist of a single layer of X gates which depend on the generated Bell state, followed by a Hadamard on the first qubit and a C0 with the first qubit as control and the second as a target. To summarize, we have covered how to use CQASM to implement 2 basic examples of quantum circuits. The first example was to generate an arbitrary qubit state, and the second was to generate a Bell state. Next time, we will cover how to implement the quantum Fourier transform.